Hello, Len Schubert here. First of all, my thanks to Loisas and Eric for organizing this timely workshop in what I'm sure is a wonderful location and for trying to help me get my message across despite my absence. I did allow 2 days for getting there and planned way ahead, but the best laid schemes of mice and men can get unglued thanks to the airlines. So what I mean by kinds of knowledge concerns both the form of the knowledge, the syntax and the semantic types, and the content of the knowledge. And by genuine understanding, I mean the kind of understanding that enables inference, reasoning, based on what has been conveyed through language in concert with background knowledge. Now, there was a great deal of initial research on genuine understanding in the 60s to mid-80s, and exciting progress was made. The greatest insight, I think, was that vast amounts of knowledge are needed for genuine understanding. So, for example, in a simple restaurant story, such as Shank and his students used to talk about, John had lunch at Mario's. The hamburger he ordered was tasteless, so he left a small tip. We're not explicitly told the answer to the questions that are on this slide, like was John given a hamburger, did he eat it, where, who gave it to him, and so on. And yet we know the answers to those questions based on script-like or schema-like knowledge that we have about the way restaurant visits usually work. Now, what brought this exciting progress to a virtual halt in the middle 80s to 90s? Well, in a word or in a phrase, it was lack of scalability. Specifically, there were, first of all, problems in the accuracy of interpretation because of the pervasive ambiguity of language. So, for example, in a sentence like, John observed the bird with binoculars, or with yellow tail feathers, with delight, with fellow birders, with its brood of chicks. We, as people, easily associate the prepositional phrase with the correct object, in this case, either the observation by John, that is, we associate the modifier with the verb, or with the object of the observation, the bird. We don't even notice that there's an ambiguity, but for machines there is severe ambiguity there, and despite some progress, this is still a pervasive problem. An even greater problem is the knowledge acquisition bottleneck. We seem to need millions of items of ontological knowledge, knowledge about familiar entities which keep showing up in various texts, newspaper texts and elsewhere, and most importantly perhaps general world knowledge, both concise lexical knowledge such as that restaurants serve meals to customers for pay, or also the more elaborate versions, the story-like versions or script-like versions as exemplified by the restaurant visit I mentioned. Perhaps a problem which has not received as much attention and which tended to kind of fade from the consciousness of the community was the expressivity of the representations used. Basically, its adequacy for language and for reasoning. So what was the solution to these problems as people saw it? Well, of course, in the 80s and 90s, there was the machine learning revolution, which assumed that statistical techniques and neural net techniques based on large corpora of text could basically overcome the scalability problems. And certainly one can see that in an example like the one about birds and binoculars, or the familiar time flies like an arrow, one can see that collocation frequencies are likely to be helpful. So if we see lots of sentences where time is the subject and where flies is the verb of a sentence, as in time certainly flies when you're having fun, then we are going to be predisposed to interpret the combination in that way, whereas something like a noun-noun interpretation, analogous to fruit flies, or an imperative interpretation, as in you shall time flies as you would an arrow, these simply don't occur except in some linguistic texts, and so they're simply not likely to be what we think of when we read the sentence. And certainly, machine learning has had significant successes, particularly where shallow methods suffice, as in the examples listed here: speech recognition, machine translation, and so on. But the problems of genuine understanding leading to reasoning and problem solving seem to be as severe as ever, despite some peripheral advances, as for example in speech recognition and parsing accuracy, and obtaining large numbers of small factoids from text on the web or other large corpora. So what are the key challenges that we still face? So first of all, we need to have semantic representations and knowledge representations that are in fact close to language and adequate for language. We need inference methods of various kinds, both soft varieties such as probabilistic or inductive or abductive methods, basically pattern matching methods, as well as firm methods, deductive methods. And we need very, very large amounts of knowledge, both pattern-like, like predicate argument patterns, schemas, which are patterns of events or relationships in the world, and also more deductively oriented axiom-like knowledge items. Now, why won't current machine learning methods solve these issues? Well, I think that's primarily because machine learning cannot invent representations. It basically can learn representations that you specify either by example or by suitable constraints, for example, on latent variables or in some other way. So, for example, you can learn classifications from annotated corpora or machine translation from side-by-side examples in two languages, and you can also even learn rules for translation if you provide a framework for the rules on latent variables, and so on. But we can't expect the machines to simply come up creatively with the right representations. We have to figure that out ourselves. Nor can we expect machine learning in its current form to lead to reasoning. So here are a couple of examples of the kind of reasoning we really need for understanding. There's a simple story here about Alicia driving home from her holiday visit to the US. Now, people can very easily answer the question what borders she crossed in her drive, assuming that they have a little bit of basic knowledge about North American geography. So we easily figure out that she must have crossed either the border into Canada or into Mexico. And there are various kinds of knowledge involved, diverse kinds that have to be brought together to make that inference, such as what's generally involved in a holiday visit to another country. You need to go into that country and you spend some time there expecting to reap some benefits, and then you go back home. And you also need to understand what home means, typically a permanent place of residence. You need to know that when you go in or out of a country, you cross its borders, that driving takes place on land, and that the only land borders that the United States has are with Canada and Mexico. So that's how we can get this disjunctive knowledge that Alicia crossed the border with Canada or Mexico, and we also infer that probably she's a resident of one of those countries. There's a still more demanding example here. When Randy learned that his metastatic cancer was terminal, he decided to stop receiving chemotherapy and enroll in a hospice program designed to provide palliative care. Now, given this story, we can easily answer the question, why did Randy decide this? And again, it needs many diverse kinds of knowledge to be able to reach human-level understanding of that little story. You need to know, for example, that learning something implies knowing it, that knowing something implies its truth. And we need to know about the typical course of metastatic cancer and what terminal cancer means, and we know what the course of chemotherapy usually is, and what medical treatments in general try to accomplish, and that stopping a process entails it was going on, and so forth. And so, at least from this information, which I've got in black on this slide, with the conclusions about Randy in blue, we can infer that Randy was confronted with this choice between chemotherapy and enrolling in palliative care, but this still doesn't tell us how Randy knew all this, and so that he could make the decision. So this requires mental modeling. That is, we need to know that the conclusions that jump out at us in such a story also jump out at others who have the same knowledge. So this is simulative inference, which is something a student of mine, Aaron Kaplan, and myself worked on some years ago. So it's on the basis of all of this that we can actually understand Randy's choice. And I'm submitting that current machine learning methods are very far from being able to learn this kind of inferential process. So let's look at, first of all, form, the expressive devices that are needed in just these simple examples. There is, of course, predication about various entities, their properties and relationships. There are temporal relationships among events. There are causal relationships, geographic relationships that may require mental modeling of geometry or imagistic kinds of things. And we encounter conjunction and disjunction. Canada and Mexico have borders with the US, and Alicia drove to either one or the other of these countries. And we encounter negation and quantification. And so already this indicates that we need at least the resources of first-order logic. In fact, the quantification is non-standard, so we seem to need a little more. But in fact, we also need quite a bit more beyond that, as indicated on the next slide. So we need genericity, that just about all of this knowledge is true about typical cases, but there are exceptions. And furthermore, we have knowledge about patterns of behavior, which also is generic, but it's more extended over multiple events or multiple relationships. These are the schemas or scripts or frames that everyone talked about, at least in the 60s and 70s. And then we have these mental notions or attitudes, learning, knowing, expecting, deciding, inferring, and so on. And very importantly, we have uncertainty, Alicia's probable home country, Randy's life expectancy, and so on. And also, we have various instances of predicate modification and sentence modification, and likewise reification of predicates and sentences, as indicated in the extracted examples here. Now, are any of these devices peculiar to English? Well, of course not. The same story could be told and understood in any language. And I doubt very much that it's a pure cultural accident that these devices are present in all languages. Rather, I think this is a reflection of our mentalese semantic types. And, there's pretty good evidence for that position, such as the conjecture held by some prominent theorists in cognitive science and anthropology and elsewhere, that language and thought arose more or less simultaneously, maybe 500,000 to 50,000 years ago. And Steven Pinker argues very persuasively that humans occupy the cognitive niche in the world thanks to their symbolic capabilities expressed both in their thinking and in their language. And Richard Montague showed that there's a very tight and elegant relationship between linguistic phrase structure and meaning, which surely is not simply a cultural accident. So certainly it seems reasonable to me to view language as a mirror of mind, and we need the same expressive devices that we have in language in our internal representations if we're going to model human-like genuine understanding. Now, I talked at AAAI in January about a wide variety of semantic representations that have been explored, and I'm not going to reiterate what I said here, so this slide just summarizes in a sort of caricature way what I said there. But the overall picture is that most of these representations are either expressively inadequate for language and for common sense reasoning, or they are inferentially inadequate, often because of a lack of attention to semantic types. And I also mentioned in that talk that the episodic logic development, which I've been working on with my students for many years, tries to remedy many of these flaws. And I'm going to briefly indicate here what these representations in episodic logic look like. This is a Montague-inspired first-order representation, very close to ordinary language, as indicated by the examples in green, which are the interpretations of the sentences in blue. So we have John donated blood to the Red Cross, and I indicate an initial representation there in green, which then gets elaborated by scoping of quantifiers and other operators and explicit introduction of event variables. And this gets regularized or canonicalized further by scolemization, that is, introducing names for existential variables and also definite variables, and by splitting conjunctions and other operations. And so here I have indicated the two formulas that result from that sentence. And then there's a second sentence that is chosen to illustrate the expressive capabilities of episodic logic. Very few people still debate the fact that the Earth is heating up. This leads, in these stages indicated above, to three facts. First, a named fact, and then an identity for that fact. It's equal to a certain proposition, namely that around now the Earth is heating up, and then a quantified sentence that very few people still debate that fact. Now, these particular cases are handled by our machinery, but unfortunately the machinery is very error-prone still because of often errors in syntactic parsing and also inadequacies in the distinctions made by current syntactic parsers among semantically distinct entities. Most of all, of course, we lack the knowledge to actually make any inferences about these cases unless we explicitly supply it. But in principle, we can make the inferences as indicated on the next slide, the epilogue system for episodic logic, which also has been under development for many years and consists of a central reasoner and a number of specialists that support the reasoner, and I've indicated here some logical input as interpreted from English and output, which would be inferred if the relevant background knowledge is present. What I really want to point to here is a common misconception about rich expressive devices in a representation language, namely that this leads to intractability and poor performance of reasoning systems. That's simply not the case. And we demonstrated that, my student Fabrizio Morbini and I, in a paper that's, by the way, referenced at the end. I have a list of references there, showing that we could, in fact, match the performance of current FOL systems attuned to FOL problems, particularly if we had relatively large knowledge bases. So here are just some examples of the kinds of inferences that Epilogue is capable of if it has the correct interpretations and the right background knowledge. And this is taken from James Allen's and George Ferguson's Monroe County emergency domain. So one example here is we are given that most front loaders are currently in use, and we would like to make the inference that therefore most front loaders are currently unavailable. And this basically just needs some lexical knowledge about the relationship between being in use and being available. And and this is formulated for equipment, and also we know that front loaders are a type of equipment. The second example is a slightly more difficult one. Alice found out that Mark Twain is the same as Samuel Clemens, from which we want to make the inference that first of all, Alice didn't know before finding out that that was the case, and that she knew it afterwards, and that it is a fact, because finding out is one of those implicative verbs that entail the truth of their argument, which is the proposition that here Mark Twain and Samuel Clemens are the same. And so we actually find out that they are the same. And this is a more complex example from the Monroe domain. Every available crane can be used to hoist rubble onto a truck. The small crane, which is on Clinton Avenue, is not in use. And so we want to infer that we can use the small crane to hoist rubble onto a truck. And I'm not going to trouble you with the details. I just want to point at the bottom of the slide to the representation of the question, which, if correctly interpreted, leads to a very fast inference in the fraction of a second that in fact the small crane can be used for this rubble hoisting task. So what kinds of knowledge do we need to deal with language broadly and with dialogue and with common sense inference? Well, first of all, I claim that we need tens of millions of simply patterns of predication. Just not really facts, but just the patterns of argument types and predicates that go together, such as persons seeing birds, seeing with viewing instruments. Note that this is a little more abstract than simply word collocations, word co-occurrences. Birds with feathers, tail feathers, colored feathers. This would bias us towards the reading of seeing a bird with binoculars or a bird with yellow tail feathers. We also need many millions of patterns of events and of relationships, and here I've indicated the kind of syntax we are working on in a slightly simplified fashion for patterns of events for going on a visit to a foreign country for some benefit. And so there are a number of steps involved. This is a lot like scripts or like plans as they've been used in AI, but it uses the very expressive episodic logic representation for the propositional parts. And then we would also have those kinds of patterns for what happens with a cancer patient and what happens in surgery and chemotherapy and so on. And also we need lots of object utility knowledge, because we think of that instantly when we see talk about an apple or a pen or a car. We immediately expect their use in particular ways. and also dispositional knowledge about what dogs are disposed to do, what fragile objects will do when you drop them, and so on. And these patterns generally lead to a kind of inference where if we see some or more parts of the pattern, then we tend to infer that the whole thing has taken place or is taking place. We also need lots of lexical knowledge and paraphrase knowledge about dogs being mammals, pens being writing instruments, killing causing the victim to be dead, and walking taking place on foot, and then that selling something has a converse representation of buying something, and that making good money can also be phrased in terms of earning well, being well compensated, pulling in the bucks, and so on. And we have various conditional kinds of generic knowledge. If you drop an object, it'll hit whatever is beneath it, and dogs are generally friendly, and so on. And we also need special kinds of knowledge about taxonomies of things and the parts of things and how things are typically related, how events are related in time, and about arithmetic and sets and geometry and imagery and so on. So how can we get at all of this knowledge? How can we address the knowledge acquisition bottleneck? Now, certainly we have lots and lots of textual knowledge out there, unstructured text, but how do we actually turn this into inference-enabling knowledge? We can get out schematic pattern knowledge to some extent by statistical techniques, but it generally is not adequate for actual inference of the kind that I've talked about. So we've attempted various approaches to breaking through the knowledge acquisition bottleneck, and rather than going through this list here, let me jump to the next slide, where there's, first of all, a schematic for the K-next architecture, extracting knowledge from text. So we start with a parse, and that is a phrase structure parse, a tree bank style of parse. And the example here is, I had a terrible flu last year. Then we compositionally interpret this phrase structure parse using a kind of expression matching, regular expression matching to the right-hand sides of phrase structure rules, and at the same time we abstract simple propositions from that, and we end up with abstracted formulas like the ones at the bottom, which have been rendered into a simple English automatically. A person may have a flu can be terrible. And so we get very many of these. We have extracted millions of these, and the next slide shows the K-next website in a screenshot for the example where we've probed this site for person and car, and so this shows the relationships that we have gathered about typical relationships that we find between persons and cars, like having one or driving one, and so on. And on the right, I also show recent work, and this is by Jonathan Gordon, he's now postdocing at ISI with Jerry Hobbs, in which he strengthened these simple propositions into quantified propositions that can enable certain kinds of inference. So, for example, from a person may have hair, he gets the stronger formula that all or most persons permanently have some hair as a part. And so if you're given something like Dana is a person, we'll draw the inference using epilogue that probably Dana permanently has some hair as a part. And there's also more dynamic stuff, such as if given that Acme is a company, we can make the inference that probably Acme occasionally announces a product. But unfortunately, this is still far from enough for actual language understanding. And on the next slide, I show several additional efforts at knowledge acquisition that we've undertaken. So there are There's been a lot of knowledge engineering of primitive verbal concepts, VerbNet classes in a sort of semi-automated way, automated axiom extraction from WordNet, where, by the way, it's important in abstracting axioms from the nominal hierarchy to make distinctions between just the kinds of nominals involved, and there are various properties that we look at, especially whether there are mass or count. So, for example, from the pair that's a hypernym pair seawater water, we get the axiom that all seawater is water, but from the pair gold noble metal, we get that the kind of stuff gold is an instance of a noble metal, and that's an important logical distinction. And we're also working on fully interpreting the glosses in VerbNet, and perhaps most interestingly, we're working on using graphical modeling for understanding certain aspects of first reader stories. So, for example, in the story that Rosie and Frank see a nest in the apple tree, we can make the inference that they can't see whether there are eggs in the nest. I mean, imagine two kids standing under a tree and seeing the nest, and we easily understand that they won't be able to see whether or not there are eggs in the nest. And it's because of occlusion of the eggs by the nest itself, and that's quite a tricky relationship, and those kinds of occlusion relationships can be handled by geometrical modeling, and we have a paper on that that's also listed at the end. And we're also currently doing preliminary work on finding the right kind of syntax for a broad range of patterns of events and patterns of relationships that subsume traditional scripts and schemas and plans and the like, and also use the fully expressive episodic logic representation. And we're also thinking about how these can be learned from prototypes, certain kinds of primitive schemas, if you like. So as my conclusion, I would re-emphasize that for accurate parsing, we seem to need lots and lots, many millions of patterns, semantic patterns that relate predicates to types of arguments, modifiers to predicates, in order to get correct parsers and hence correct interpretations of what has been said. And expressive adequacy is more or less achieved by the episodic logic representation, although interpretation into that representation is still brittle, and we need inference methods beyond those of first-order logic, and they've been implemented in Epilogue, and they include natural logic-like representations, but go beyond that. The examples I gave from Monroe County, for example, are well beyond the natural logic techniques that have recently received a lot of attention. And there are some probabilistic techniques as well, but they remain rather ad hoc, and this is something we're working on very much. And I hope that more people than currently will be working on the knowledge acquisition bottleneck, particularly in ways that provide knowledge that is inference enabling in the sense that I have urged is required for genuine language understanding, including soft inference and deduction and abduction and so on. Thank you very much.